Hello, today we will deal with internal forces in Gerber beams, that is, in hinged beams. I will show you how to solve a Gerber beam with two examples. I will solve the first example by breaking the Gerber beam into simple beams, and I will do the second example without breaking it into simple beams, just simply calculating the beam we get with hinges without breaking it into simple beams, because that can also be done. But also the problem statements vary, and some of them simply require us to break the Gerber beam into simple beams and then calculate it, showing that we can do it rather than just solving the beam as we know how, but rather as imposed. At the beginning, a brief introduction. This will be the first example. We need to draw the shear force diagrams in a continuous beam and solve the problem by breaking the beam into simple beams. The beam is quite complicated with 3 hinges here. 1, 2, 3, 4 fixed non-sliding supports, and 1 fixed support with sliding. Now we need to think about how to break this beam at the hinge. So if we have 2 parts of the beam connected by a hinge, it will be equivalent if we break this element at the hinge into 2 parts. In these 2 parts, the reactions will be opposite, action-reaction. So if the reaction here is upwards in one beam, in the other, it is downwards. We can switch that, meaning it will be downwards here and upwards here. It's important that they are simply opposite. The same goes for the horizontal reactions. Just one more important thing. When we solve Gerber beams, it is generally recommended to simply make a diagram of normal forces, that is, horizontal forces, without breaking the beam into simple beams. Only then do we break the beam, and at that point, we ignore these horizontal forces. We only focus on vertical forces. And that's exactly what we will do. So as I mentioned in the previous video, if you were watching, the diagram of normal forces is rather straightforward when it comes to Gerber beams. So I also have examples here where we do not deal with those normal forces. Because as I said, it's quite a simple matter. So we already know that we will break the hinge this way. And now if there is a shear force applied at the hinge, we only write that shear force in one setup. It can be in the top setup, but it can just as well be in the bottom setup. Here we also have freedom, and when it comes to the applied moment, it must be clearly applied from one side of the joint, either from the right or from the left. Then we do not have a problem determining to which beam it should be transferred later. And the principle is as follows. We can solve a straight beam if the unknowns are either 2 vertical forces and a horizontal force, or 1 vertical force, a moment, and a horizontal force. So we look at a Gerber beam, we imagine, that we divide it at the joints, meaning that a vertical reaction occurs at this joint, and we consider which beams will be primary and which will be secondary. Generally, beams with a greater number of reactions will be higher, and these will be simple primary beams that are at the very top. There may be some equivalent beams. If there is a joint support and a wheel joint below it, it divides the beam into 2 equivalent ones. Having already calculated the reaction from the higher beam, we transfer it with the opposite direction to the lower beam. These are examples of primary beams, simple beams, which we can solve, meaning we have 2 vertical reactions. We do not need to have a horizontal reaction, but we have 2 vertical ones. So by calculating the sum of moments here, for example at this point, we can immediately calculate this reaction, then the sum of projections on the y-axis, and optionally the sum of moments at this point, and we have it calculated. The second example, here we have 2 vertical forces and a horizontal force, which is exactly what is here in the first point. Here as well, the sum of moments at point A, we have calculated Vp, the sum of projections on the y-axis, and we have Va, and the sum of projections on the x-axis, and we have Ha. And here is another example, vertical reaction, horizontal, and moment. This is also a beam that we can solve immediately. And now beams that cannot be solved without first calculating the reactions from the higher beam at the joint. Because here, you see, we have 3 vertical forces and a horizontal force. So if we wanted to calculate it, we could, for example, take the sum of moments at this point. Well, in this equation of the sum of moments, there would be 2 unknowns, Vp1 and Vp2. If we made the sum of moments here, it would be Va and Vp1 unknowns. And then with these unknowns, there's nothing we can do. We will do the sum of projections on the y-axis, and we have 3 unknowns in this equation. So this is a beam that we can arrive at, but only after we calculate either the reaction at one joint or in the second joint from the main beam. And here is yet another situation that is not immediately calculable. That is, we have a moment, a horizontal force, a vertical one, and yet another vertical reaction. So here the same situation, it is not a calculable beam. We can only calculate such a beam when we determine the reaction from the main beam at this joint. All right, and I think that's enough of such a brief theoretical introduction. Let's now move on to solving our example. So we have our case and we are considering which beam will be the main one. So we are thinking, breaking it down at the joint into 1, 2, 3, 4 beams. If we break it down. All right, let's look from the right side. Here we cut the joint. We have a vertical reaction at the joint. So on this beam from P3 to F, there will be one vertical reaction, a second and a third. All right, so it is not determinable. Let's look at this from P2 to P3. One vertical reaction, a second vertical reaction, and a third vertical reaction. It is not calculable. The beam P1, P2. Here there will be one vertical reaction and a second vertical reaction. Okay, this one is calculable, so this will be the main one. And let's also look at the beam AP1. Here we have a moment, a horizontal reaction, one vertical reaction, and a second vertical reaction from the joint, which is also not calculable. Because there are two vertical reactions and a moment. And we remember from the previous slide, you can have either two vertical reactions and a horizontal, or a moment, horizontal, vertical. And here there is a moment, horizontal, vertical, and yet another vertical. So this is an immediately non-calculable beam. So this beam P1, P2 will be at the top. Once we calculate P1, this beam will already be calculable, because we will have a vertical, a horizontal, and a moment. Okay, so this one will be right below it. And this P2, P3, once we calculate P2 here, we will have two vertical reactions. So we can calculate this. Okay, and if we calculate this beam P1, P2, will we be able to calculate the beam P3F? Well, no, because to calculate it, we need the reaction at the joint P3. So this beam will be at the very bottom. Once we solve P1, P2, we will be able to calculate both of these simultaneously. And once we calculate this one, only then will we be able to calculate this one. So this is beam 1, 2, 3, and beam 4. We will solve them in this order. Here, the second or third beam, the numbering will be arbitrary. And you see the reaction VP1, here is the counter reaction from VP1. I did the same in each joint. I accepted that this 6 will be on this beam. I could just as well have accepted it on this one. It's arbitrary. And I clearly had the moments marked on the beam on the left. And that moment could have been at the node, so there is no problem here. And I marked all the reactions. We can start calculating. So we begin with beam 1. Note here that there is also a concentrated force of 2 kN, in addition to the continuous load. The sum of moments at the first joint equals 0. So we have 2 times 2 meters from the continuous load. 2 times 5 times 2.5 comma minus VP 2 times 5. I am not calculating the resultant here. If you have a problem with this, but from the previous videos, I think you should know what it's about. From this, I conclude that the reaction VP2 equals 5.8 kN. The sum of projections on the y-axis in this first beam equals 0. So VP1 minus 2 times 5 plus VP2. So plus 5.8 comma equals 0. VP1 is 6.2 kN. Beam 2. The sum of moments, beam 2, that is this one. And here we start, either sum of moments at point A or point B. To calculate it for yourself. Actually, if we start at point A, it will be an unknown moment and VP1. This is not an effective equation. It is better to first do the sum of moments at point B. Then we directly calculate MA. And then the moment at any point. Or the sum of projections on the y-axis, and we will have the reactions. Okay. MA plus 4 times 3 minus 2 times 3 times 1.5, plus this moment, 2, plus 6.2, comma, so the reaction VP1 at arm 2. I take right-handed moments as positive, as always. The moment at point A equals minus 17.4 kNm. So, as you already know, I change the direction of this reaction immediately. The direction of this moment to the opposite. And here I make a plus. So we have calculated the moment. The sum of projections on the y-axis equals 0, so we have 4 minus 2 times 3 plus VB, so plus VB. Minus 6.2, comma, so this from the joint equals 0. VB equals 8.2 kNn. Beam 3. Let's take a look at the third beam. The sum of moments at the third joint equals 0. So we have this, minus 5.8, comma, which is VP2 at 4 meters, plus VD at 2 meters, plus 4 equals 0. VD is equal to 9.6 kNm. The sum of projections on the y-axis equals 0, minus 5.8, comma, plus 9.6, comma, which is the reaction, VD just calculated. Minus 6 plus VP3 equals 0. Therefore, VP3 is 2.2 kNm. And now we move on to the last beam, the fourth beam. The sum of moments either at point E or point F first. I will do it at point E. Minus 2.2 times 2 minus VF times 1 equals 0. VF overall equals minus 4.4. VF is not in that direction, but in this one. The sum of projections on the y-axis equals 0. Minus VP3, which is minus 2.2, comma, plus VE minus 4.4. From this, VE is 6.6 kN. And now as we move on to drawing the graphs, now we already have the reactions calculated. We can draw the graphs just like in the previous video. Just the fact that this is a Gerber beam gives us the information that the moment at the joint must be 0. This is also important information because if it does not zero out, it means we are calculating incorrectly. And it will turn out soon that all those reactions we calculated, that is VP1, VP2, and VP3, are actually unnecessary. And it is possible to solve a Gerber beam without calculating this, without breaking it down this way, but that will be in the next example. So we are moving on to drawing the graphs. I have already marked the reactions here according to the directions I calculated. The moment too. And now we draw the shear force. Here we have 4 kN. Then we have the resultant of 2 times 3, which is 6, so we go down to minus 2 from the other side. A jump of 8.2 kN, so up to 6.2. I don't know, it seems to me that the scale will not be kept, but oh well. 6.2, comma. Then in this part of the beam we have no shear force, so the value does not change. Next, yes, here we have to split. Because there is a force applied, it's a characteristic point. So we divide this continuous load into 2 parts and write down the resultants from the 2 parts. So 2 times 2 is 4. If anything is unclear, I encourage you to watch the previous video where I do it a bit slower and try to explain everything. 3 times 2, which is 6. And now we go down from 6.2 by 4 linearly to 2.2. Next, we have a jump of 2 down, 2.2, comma, I'll write that here. So as 2 down, we are at 0.2. Then from this 0.2, comma, we go down 6 linearly towards the negative, so we will be at minus 5.8 on the other side. So we are at minus 5.8. Now there is no shear force here. We are only going to that support. I did not mark it with a line, meaning I did not extend this graph. All right, 5.8. Next, we have a jump of 9.6. So we calculate now minus 5.8 plus 9.6 equals 3.8 on the other side. $3.8. Then here in this section, there is no shear force, so we move without changing the value. And now from 3.8, we jump down 6, meaning 3.8 minus 6 equals minus 2.2. It could be like that. Next, again, there is no change. I again did not mark the interval. And here we have a jump of 6.6, so plus 6.6 equals 4.4 on the other side. Jump, we are moving without change. 4.4 is okay, it is calculated correctly. Because we end at a value of 0. And this is the shear force graph. As you can see, we did it efficiently. We calculate the areas of the figures. So here we have 4, here we have 2. You can calculate this using the similarity of triangles. You can notice it simply. So here it will be. The value changes by 6, and here it changes to zeroing by 4. That's 2/3 of what is here. 2/3 of 3 is 2. But you can calculate it in whatever way you know. So that's 2. All right, that's the area in that case. 4 times 2 times 1/2 equals 4. The area of this is 2 times 0.5 times 1, which is 1. The area of this is 6.2 times 2, which is 12.4. Now this area, here we have a trapezoid that looks like this. So we have 2.2 plus 6.2 equals 8.4 times 2 divided by 2. That is 8.4. Next, we need to calculate the 0 point. Yes, let's do that. All right, I will try not to mess this up too much. Let this be x, so 5.8 to x. 5.8 to x is like 0.2 to 3 minus x. From this, it turns out that x is equal to 2.9 m. Now we calculate the areas of the triangles. We have 2.9 times 5.8 times 1/2, which equals 8.41. The area of this is 0.2 times 0.1 times 1/2, which equals 0.01. The area of this rectangle is 5.8 times 2, which equals 11.6. Here we have 3.8 times 2, which equals 7.6. 2.2 times 2 equals 4.4. And 4.4 times 1 equals 4.4. And when drawing the moment diagram, we remember that if there is a concentrated moment applied to the beam, there is a jump in the moment diagram equal to the value of that moment. So here we have the 17.4 kNm, which pushes the diagram upwards. So we start with an initial value of 17.4. And we know that in the end we must finish at 0 because there is no external moment applied. So that is a negative value at the top. Next, we have a jump of 4 in the positive direction, and since here on the Q diagram it was linear, on the M diagram it is a parabola. So up to 13.4 at this point. 13.4, then up by 1, so up to 14.4. So the diagram looks like this. This is a parabola. 13.4, 14.4, minus, minus. This is the extreme value here, because there is a sign change. So we have an extreme value here, and it will be the same at this point. So, all right, we are at negative 14.4. Now 12.4 in the positive direction linearly, so up to 2 linearly, which means we are still at a negative value. And now be careful, it's easy to overlook this here. We must always remember when drawing the moment diagram about these moments that are on the beam. Because when drawing the shear forces, we are actually based only on those shear forces that are on the beam. But when drawing the moment diagram, we focus more on these areas here, rather than looking at the beam. It's easy to make a mistake here. So we have a jump of 2, because this moment on the beam is 2 kNm and it is in the positive direction. So from this 2, we are now at 0. And this is the principle of Gerber beams that we must actually come to 0 at the joint. So we must remember that we also need to reach 0 here. Of course, this must arise from the numbers. And we must also reach 0 on the moment diagram at the joint. All right, 8.4 in the positive direction. So I didn't draw the interval here either. 8.4. And we are moving parabolically because here we were linear. So plus 8.4. Now we have 0.01, continuing parabolically gently to that extreme. We added only 0.01, so we are at 8.41. This is an extreme value because here we had a sign change. And now we have the area 8.41, which is negative. So from this positive 8.41 to the negative 8.41, that is to 0. And to that second joint precisely. Next, 11.6 linearly in the negative direction. And now we have a moment of 4 applied here at this point on the beam. It is also positive, so to 7.6, and we linearly go down to 0 with this field of 7.6. That is to the joint. Here it is 7.6. Next, 4.4 in the negative direction, meaning upwards. And then 4.4 down to 0. So we are already at, oh sorry, that didn't go well for me. Cut linearly. It's not easy to draw with these PowerPoint tools. We are. All right, we have the shear force diagram, we have the moment diagram. We managed with this Gerber beam. If you think the material was helpful, I encourage sharing it with colleagues. I recommend subscribing to our YouTube channel, file on Facebook and Instagram. And for now, that's all. I wish you pleasant studying. Best regards. Goodbye.